Hello again. I've gotten a request to show how to draw a load shear moment diagram when the shear expression has a quadratic term, has an x squared term in it. So here you go. What I've got here is a beam that's pinned on the ends and has a distributed load of 3,000 newtons per meter down on one end, tapering to 0 on the other end. Now, in your books, you'll probably see this kind of distributed load drawn with the line vertically, or the distributed load up above the beam, and that's certainly correct. I find out that I mess up a lot less often when I put a downward load below the beam. It makes it easier for me to keep track of, and I'm going to suggest you might experience the same thing. So what we're going to try to do is figure out the loads across the beam and use that, along with integration, to draw a load shear moment diagram. Well, first thing I need to know is the reaction forces at the ends of the beam. I'm going to call that point A and that point B. And as always, unless I have a pretty good reason, I'm going to use that as my positive sign convention. All right. Well, first thing I'm going to need to do is draw the free body diagram. Okay? If you're solving a problem like this and you're not drawing a free body diagram, you should be thinking to yourself, why isn't there a free body diagram on this sheet? You're going to mess up a lot less often when you put the free body diagram down there. Invest the extra couple of minutes. It's going to be worth it in the long run. So what I'm going to do here is I'm going to take this. I have an upward force. I'll call that FA and FB at the ends. All right. Sketch that in there. There we go. FA and FB. Now, I can go ahead and integrate this if I want and treat this as a distributed load, but for the purposes of finding the reaction forces at the end, it works just as well to concentrate this load. The pins at the end of this don't know necessarily that that's a concentrated or a distributed load. If I replace it correctly with a concentrated load, I'll get the same answer. Now, the beam itself does know that's a distributed load, so this only goes about so far. But what I've got here is a concentrated load, and I'll call that FC, and it's applied at the centroid of the distributed load, which, since it's a triangle, is 1/3 of the way from the big end. So that's 1 meter. All right. And the concentrated load's magnitude is the area of that triangle here. So it's 1/2 BH. So it's 1/2 times 3 meters times 3,000 newtons per meter. So I'm going to get 4,500 newtons down. All right. Now I want to keep this video short. If you sum the vertical forces and then sum the moments about one of those points, either A or B, you're going to find out that FA equals 3,000 newtons and FB equals 1,500 newtons. Okay? At that point, we're ready to go ahead and write out an expression that describes the load all across the beam. Now, I need to know L of X, which is that line right there. Well, it's easy here. If we start our coordinate system there, that's 3,000 newtons. I'm sorry, minus 3,000 newtons. Let me try it again. Minus 3,000 newtons plus 1,000 newtons per meter. Okay? That's the equation for that line right there. Once we have that, we're in good shape. Okay, well, let's write out the shear expression. Well, let's call that V of X, and that's going to be V0 plus the integral from 0 to X, L of X dx. Okay. V0 is the shear at the end, which we know right now is 3,000 newtons. Now, the units of shear are newtons, right? The units of that are newtons. The units of L of X are newtons per meter. So how do I reconcile that with that? Well, dx has units, okay? It's a little itty-bitty number. That's the whole idea of an integral. This is an infinitesimally small number, okay? It is not 0, and it has units. It has units of length, all right? So that's going to be times meters. Well, newtons per meter times meter equals newtons. So that integral there has units of newtons, which is compatible with that, which is compatible with that. So we're good. So V of X equals plus 3,000 newtons. I'm going to leave the units out of this just to keep it simple. Minus L of X, which is sorry, let's try this again here. Minus, plus, I'm sorry, the integral of L of x, which is minus 3,000, plus 1,000 x dx. So that right there is L of x, okay, which is what we've got right there. That's good. Let's integrate this now. This is just a polynomial, so this is easy to integrate. 1,000 minus 3,000 x plus 500 x squared. Now, if I do that right, I should get, let's see, minus 1,500 newtons when x equals 3, because that right there is 1,500 newtons, and they better cancel out. If you work this out, let's see if I got this written out. Oh, I do. It was minus 1,500 newtons, so that is the correct expression. Now, to make room here, what I'm going to do is I'm going to take this expression and write it over there. All right. Let's see. Okay, that's an ugly 2. Let me fix that. And get rid of all that stuff. Okay, so we're halfway home. We've got the shear expression written out. Now we need the moment written out. Well, the moment is the integral of the shear. Shear is integral of the load. So we'll do this. It's m0 plus integral from 0 to x, v of x, dx. Now, two things I want to tell you about. First thing is, I'm writing the integral from 0 to x. How come I'm doing that? Why am I not going from one number, 0, to another number, say 3? Well, if the lower and upper integration limits are fixed numbers, what I'm going to get out of the end is a number. It's going to be an area underneath the curve from 0 to 3, say. I don't want a number, I want a function. Okay? If I want a function, then I can integrate from 0 to x. Right? The other thing I want to tell you about is units again. Well, this is going to be in Newton meters. That's the definition of moment in the metric system. M0 is going to be in Newton meters. This is newtons, and again, dx is in meters. So newtons times meters. So the units are going to work out. Now, the nice part about this being a pin-ended beam is that the definition of pinned means there's no moment at the end. So because it's pinned, that has to go to 0, and all I need now is to integrate from 0 to x that expression right there, which is 3,000 minus 3,000 x plus 500 x squared dx. Again, real easy to do. So I'm going to get 3,000x minus 1,500 x squared plus 500, over 3 x cubed. Ready to go. Now, if I do this right, the moment at x equals 3 had better be 0, as had the moment at x equals 0. Well, let's check this out. M of 0 equals, let's see, 0 minus 0, okay, that's 0. So that's a good check. And m of 3, if I do this right, I should get 0. And I actually worked this out. I got something times 10 to the minus 13. So that's 0. So there you go. There's load right there with the two concentrated loads at the end, shear right there, and moment right there. So there's your load, shear, moment expressions, and you can plot these to make the load, shear, moment diagram. Now what I'm going to do after this is I'm going to go on to MathCAD, and I'm going to show you how to do this same operation in MathCAD and plot the results.